Hello everyone, and thank you for joining today's ReproducibiliTeach video. My name is Tracy Weisgerber, and I am a meta-scientist at the Quest Center for Quality Ethics, Open Science, and Translation in Berlin. So today we're going to talk about why you shouldn't use bar graphs to present continuous data and what type of visualizations to use instead. We'll talk about how to choose the right type of visualization based on the characteristics of your data set, and we'll also talk about how to make those different types of more informative visualizations effectively. Before we get started, I wanted to begin with a little reminder from the tips and tricks videos about the goals of effective figures. So our effective figures should do three things. The first is that they should immediately convey information about the study design. So by looking at your figure, I should know whether your goal of your experiment was to compare different groups, or perhaps you have longitudinal measurements where participants completed the same measurement at different time points and you want to examine change over time, or many other different designs. And because your figure is illustrating the study design, readers should also then be able to confirm that the statistical analyses that you've used are appropriate for that study design. The second goal of figures is to illustrate important findings, and I think this is the thing that most of us focus on when we're designing our figures or thinking about our visualization. But there's a third point that's really important, and that is to allow the reader to critically evaluate the data. This is what sets science apart from marketing. We need to be able to critically evaluate each other's data in order to build on other people's experiments and create new knowledge. And this is one of the places where the improper use of bar graphs to create continuous data creates real problems, because those graphs only show the summary statistics and they don't allow us to critically evaluate the data. So let's talk about this in more detail. My interest in the problem with bar graphs comes out of my experience as a physiologist and as a scientist when I was researching the pregnancy complication preeclampsia. And one of the issues with preeclampsia is that women end up with a similar set of symptoms at the end of pregnancy, but they get there in very different ways. Some women have pathophysiology in the placenta. For other women, they may have pathophysiology involving the fetus itself. And for some women, they have maternal risk factors. And some women may have a combination of all of those things. And there may be different pathophysiological pathways that are activated within each of those maternal, fetal, and placental pathways. And so this is really a problem, because it means for any pathophysiological process we look at, we expect it to be perfectly normal in some women with preeclampsia, but very abnormal in other women. And the field right now is focused on identifying subgroups of women with preeclampsia who have specific pathologies so that we can match treatments to those pathologies. The problem with this is that data were often presented in bar graphs, and there are no subgroups in a bar graph. So bar graphs only show summary statistics. They collapse everyone into a single average, and that subgroup information is really missing. So bar graphs are what we show when we want to conceal heterogeneity or group differences. When we want to reveal that information, we need to use more informative graphs. So this is what triggered me to start working on what later became our 2015 paper that was published in PLOS Biology, where we looked at the inappropriate use of bar graphs to present continuous data in physiology papers. This paper was viewed more than 100,000 times in the first month that it was published. And it's since gone on to contribute to policy changes in a variety of journals, and some early adopters here that implemented policies asking authors to replace bar graphs of continuous data with more informative graphics were PLOS Biology and the Journal of Biological Chemistry. But many other journals have now implemented policies as well. We also know that there are editors and reviewers that use this paper or our other papers when they're requesting authors improve their data visualizations during the revision process. And this paper was also one of the factors that contributed to the Bar Plots Kickstarter campaign, which targeted editors of neuroscience and general science journals to encourage them to adopt more informative data visualization practices and implement policy changes. So what was included in the paper? Well, we looked at 700 papers published in all the top 25% of physiology journals over a 3-month period, because that's what jet lag and transatlantic flights are for. And we found that almost all of those papers were using bar and line graphs to present continuous data. So 85 or 86% of papers had a bar graph, 61% had a line graph. When it came to more informative graphics that provide more information about the data distribution or the sample size, those really weren't used very often. So only 13% of papers had a dot plot, whereas 5 to 8% had a box plot or a histogram. We also found that sample sizes were very small, in most cases less than 10 independent observations per group. In 78% of cases, bar graphs, the error bars on those bar graphs were being used to provide information about the precision of the mean or the standard error. In only 16% of cases, the bar graph error bars were used to show the standard deviation, which tells us about the variability in the data and the amount of overlap between groups. And lastly, we found that this practice of presenting summary statistics in bar graphs was so ingrained that more than 50% of papers that used non-parametric analyses presented continuous data as that they had analyzed via a non-parametric analysis as a mean and standard error or a standard deviation. And this is really a problem because non-parametric analyses are often used when either the sample size is too small to know the data distribution, or we know that the data are not normally distributed, and hence the mean and standard error or standard deviation are likely to be misleading. So you might be wondering, have we solved the problem yet? That paper came out in 2015, and many journals have implemented policy changes since then. We had a look in a follow-up study at the field of peripheral vascular disease in September 2018. And so here we looked at all papers published in the top 25% of peripheral vascular disease journals. And unfortunately, we found that the problem definitely isn't solved. So we observed that 48% of papers that had a data figure included a bar graph of continuous data. And that meant that these graphs were by far the most common type of figure of all of the different types of figures one can use to visualize data. And that also meant that they were the most common data visualization problem. More recently, we used an automated screening tool to do an analysis of open access papers in PubMed Central, and we did a random sample of open access papers in 23 different fields across a 11-year period from 2010 to 2020. And this is just the data for 2020. And what we found was that there are many fields where 40 to 60% of papers are still including bar graphs of continuous data. So you can see the red bars show the percentage of papers that had bar graphs of continuous data for each field, and then the gray bars show the percentage of papers that had more informative alternative graphs, like a dot plot, a box plot, a violin plot, or a histogram. And you can see that in fields like complementary and alternative medicine, pharmacology, biochemistry and cell biology, physiology, genetics, oncology, microbiology, and immunology, more than 40% of papers are still using bar graphs to present continuous data. So you might be wondering, if this practice is so common, is it really that big a deal? Why is it a problem, and why shouldn't I use a bar graph to present continuous data? Well, the reason is that many different data distributions can lead to the same bar or line graph, and the actual data points might suggest different conclusions from the summary statistics alone. So this is a figure from our 2015 paper, and here we have 4 different data sets that might give one the same bar graph shown on the left in panel A. The first thing we can see from this paper is that, or from these visualizations, is that all of these data sets are very small. So there's a lot of uncertainty here in the summary statistics, and the conclusions might be quite different if we had a larger sample. We don't know. So right away it tells us there's more uncertainty than the bar graph might suggest. But if I look at the data points themselves, when I look at panel B, I see that the distributions look reasonable. The second group appears to have slightly higher values compared to the first group. And this might be a small difference that I'm interested in exploring further. When I look at panel C, I see that there's an outlier in the second group that might be driving values in the second group higher. And maybe this is a difference that I'm less interested in exploring. In the third data set, there's some suggestions that I have two different subgroups of observations, one with higher values and one with lower values. Now, the data sample size here is far too small to determine whether the data distribution is actually bimodal, whether there are two subgroups. So I would want more observations to determine whether there are two subgroups or not. However, if there are, I would want to know whether there's some variable that I've overlooked in my analysis that might explain these two different subgroups. So for example, do males have lower values than females? And if that's the case, then I would want to capture that variable in subsequent experiments. And then in the last panel, we have unequal sample size. So values for the second group are clustered at the high end of values for the first group. And the issue here is that the sample size for that second group is much smaller, so I may have underestimated the variability. I would want a larger sample size here to know whether those trends hold up. And lastly, I've included p-values for a variety of statistical tests below the figure, so we can see that we can't distinguish between these different scenarios based on p-values alone. There is really no substitute for seeing the actual data points. So the next question that I often get is, okay, well, let's say I know that my data are normally distributed. Can I use a bar graph then? And the answer is unfortunately no. And there are a couple of different reasons for this. The first is that main point we talked about at the beginning, that figures need to be able to allow you to critically evaluate data. And unfortunately, the bar graph doesn't allow you to do that when you're graphing continuous data. So we can't see any information about the data distribution beyond the summary statistics or the sample size. The other issue that we have is that the bar graph often distorts our perception of the range of observed values. And so here on the left, you can see we have a bar graph showing mean and standard error. And we have a large zone at the bottom of the graph where there don't happen to be any data points. Now, with some data sets, you will have a zone like this because the values around 0 simply aren't values that are biologically possible or physiologically meaningful. In other cases, you won't have this zone because the values around 0 are possible. But we like to call this the zone of irrelevance. When it occurs, when those values at the bottom of your graph aren't relevant or meaningful, they end up taking a lot of space on your graph, even though they'll never be observed in your actual data set. The second issue we have is that we tend to cut off the y-axis a little bit above the error bar for the highest group. And that may mean that we have data points and values that are observed in our sample, but don't appear on the axis of our graph. And we can think of this as the zone of invisibility. And so one of the things that happens when we use a bar graph is that we have this distortion with the potential zone of irrelevance and the zone of invisibility, and that visualization arbitrarily assigns importance to the height of the bar instead of focusing on what we really want to know, which is the amount of overlap between groups and how the difference in means compares to the variability in the data. So it's important to remember here that our interpretation depends on what we see. When I look at a bar graph that only shows summary statistics, I'm a passive observer. I don't know anything about the sample size or the distribution, and I can simply look at this graph here and say, okay, well, it looks like maybe the second group is a little bit higher than the other groups, but there seems to be some overlap. In contrast, when I see the dot plot shown on the right, I become an active participant. So I immediately see that the sample size is very small and there's a lot of uncertainty in this data. I can see that that second group with the higher values is even smaller than the others, and we may have underestimated the variability to a greater extent. I can see that there might be an outlier in one of the groups or other factors of the data set that are particularly important, and I get a lot more information to help me critically evaluate the data. So, what I want you to remember here is that all data presentations are a reflection of reality. Looking at your data in a bar graph or a line graph is a bit like looking at a reflection in a wavy pond. You design your experiment and you hypothesize that you will end up with a duck. And so you look at your data in this graph and you think, oh, that looks kind of like a duck. It looks like I found what I'm looking for, and that's great. But that reflection is distorted, it's missing information. So maybe the thing that you're looking at is actually a duck, or maybe it's just a very oddly shaped potato. And no one wants to waste time and money and resources pursuing what they think is a duck, only to find out later that it's in fact an oddly shaped potato. And so this is why it's important to select data visualization methods that minimize distortion and that give us the ability to critically evaluate our data.